we're going to look at acid-base properties of salts. So let's start with a salt that is neutral. The salt of a strong acid and a strong base give a neutral solution. So the arrows that we're going to use are either equilibrium arrows, reaction to the right, or products go to the left. Let's start with sodium chloride. So what you do is you break the sodium chloride into the ions. That would be chloride ions and sodium ions. You take each ion and react it with water. So chloride ion plus water gives hydrochloric acid plus hydroxide. You have a strong acid as a product and a strong base as a product. And so the products would react and go back to the left to give you the reactants. So you really just have chloride ion and you have water. Water is neutral. Sodium ion plus water. You would end up getting sodium hydroxide and hydrogen ion. A strong base is produced, so the products would react, go backwards, and you end up with water. So with each one of these, you have water. Water is neutral, and so therefore, sodium chloride would be classified as a neutral salt. Let's look at a hydrolysis that would be classified as basic. So the salt of a weak acid and a strong base gives a basic solution. We're going to look at the hydrolysis of potassium acetate. So the potassium ion reacts with water to give you potassium hydroxide plus hydrogen ion. Potassium hydroxide is a strong base, and so it would react with the H plus and go backwards, and you would have water. So really for this first one, you have water. For the second one, there should be a negative there on the acetate. Acetate plus water gives you acetic acid plus hydroxide. Because it's acetic acid, you have an equilibrium. So you've produced a weak acid. So you have hydroxide that is dissolved in water, and that would be basic. So that is why potassium acetate would be classified as a basic salt. Let's look at another example. That would be the salt of a weak base and a strong acid, such as ammonium chloride, and that produces an acidic solution. So when you get a question like this, the best way to approach it is to go ahead and take each ion and react each ion with water rather than memorize. If you memorize, you're going to forget later on. But if you know how to solve the problem, you can always do that. So you're always going to take the cation plus water, see what happens. Take the anion plus water, see what happens. So let's see how this works with ammonium chloride. So we take the ammonium ion plus water, we get ammonia plus hydronium ion. Ammonia is classified as a weak base. It's a good base, but it's still a weak base. Therefore, we have an equilibrium. So we have hydronium ion. We take the chloride and we react it with water. We get hydrochloric acid and hydroxide. You have a strong acid, a strong base. They react together and go backwards, so you have water. So in this case, you have hydronium ion in water, which is acidic. So you're going to want to practice doing these on your own. So for example, if you were given potassium chloride, you take that potassium ion plus water, you would get potassium hydroxide plus hydrogen ion. This is a strong base. The strong base would react with the hydrogen ion and go backwards, and so you have water. We did this before with the chloride ion. You take the chloride ion plus water, you get hydrochloric acid, hydroxide, and they react and go backwards, so you have water. So all you have in this situation is you have these spectator ions plus you have water. If you have water, we're going to consider that neutral, and that's why your answer is neutral. Let's look at sodium fluoride. Sodium ion plus water gives us sodium hydroxide plus hydrogen ion. Sodium hydroxide is a strong base, and so it's going to go backwards, which means that we have water. Fluoride ion plus water gives us hydrofluoric acid plus hydroxide. We know that hydrofluoric acid is a weak acid because the bond between the hydrogen and the fluoride is so strong that it does not want to break. So we made a weak acid. That means we have hydroxide that is in water. And so hydroxide is basic. Let's look at another one. Zinc nitrate. Zinc is a +2 ion. We react it with water. We get zinc hydroxide plus hydrogen ion. Now, zinc hydroxide is a weak base, so we really just have the hydrogen ion. We have an equilibrium. We take the nitrate plus water, we get nitric acid plus hydroxide. Nitric acid is a strong acid, so we're going to go backwards this way. And so we really just have water. So we have hydrogen ion that's in water. Hydrogen ion is acidic. So that's how we get our answer of being acidic. Okay, now in this case with ammonium cyanide, we have a Ka for ammonium ion and a Kb for cyanide. So let's just take them one at a time. Ammonium ion plus water gives us ammonia, which is a weak base. And so we do have an equilibrium. We have cyanide plus water. It gives us hydrocyanic acid. Hydrocyanic acid is a weak acid. So we do have, for cyanide, a Kb. So what we're saying is that the first reaction is in equilibrium. We have an equilibrium, and we have a K for that equilibrium. The second reaction is also in equilibrium. So we have a K for that. So we can't just qualitatively look at this example and decide. So in this case, what we need to do is we need to compare the Kb to the Ka. In this case, the Kb is much larger than the Ka. So what you do is you look at the exponents. This Ka is 10 to the minus 10. This Kb is 10 to the minus 5. So our Kb is definitely larger than our Ka. So what that means is we only look at the cyanide equilibrium. So we're going to just ignore the ammonium. We're going to focus on the cyanide. And when we see the cyanide in equilibrium, we see that we have hydroxide. So if we have hydroxide, that is how we decide that ammonium cyanide would be a basic salt. So in the case when you have both of the reactions have an equilibrium, you will have to be given the values and you choose the one that is larger.